about aircraft materials and processes. And one of the processes we're going to talk about, the first one we're going to talk about, is welding. And here is some pretty good welding going on, but we're going to talk about the characteristics of a good weld, and we're going to take a look at some figures in the book and talk about what a bad weld looks like and what particular welds indicate as far as why it's bad. Okay, one of the characteristics that you should know about of a good gas weld is that it tapers off smoothly, like this good weld does, into the base metal. This has got a nice, good horseshoe shape to it, and it tapers off very smoothly into the base metal. Now, another characteristic of a good weld is that no oxide should be formed on the base metal more than a ½ inch from the weld itself. No oxide should form on the base metal more than a ½ inch from the weld itself if you've got a good weld. Now, let's assume you've got a weld with a crack. If you've got cracking like this, that's obviously not a good weld. And what it means is that a part has cooled too quickly after being welded. That cracking comes because the part has cooled too quickly after being welded. Now, as a mechanic, what in general do you look at when you're examining and evaluating a welded joint in an aircraft part? Well, first of all, you want to start with the big picture. And to do that, you should be familiar with the joined parts, the proportions of the weld depth to the material thickness, and the formation of the weld. And of course, in your examination, you'd want to check some details. Details such as uniformity in the width of the weld, the penetration of the weld, the presence of any gas pockets or irregular or pitted edges, and cracks that are adjacent to the weld. Now, the FAA might ask you, should you be familiar with the likely ambient exposure conditions and intended use type of weld and original part composition when you are examining and evaluating a welded joint? Well, that's nice to know information, but it's really the responsibility of the manufacturer or of the repair shop that makes the weld. Or the FAA might ask you, should you be familiar with the welding technique, the filler material, and the welding temperature range? And again, that kind of information is important for the manufacturer or the repair shop making the weld. But as the mechanic who's going to install or inspect the welded part in an aircraft, you should be familiar with the parts, the proportions, and the formation of the weld. Now take a look in the FAA figure pages at figure 44, which gives examples of 4 different types of welds. The FAA will give you this and ask you which one of these illustrations, 1, 2, 3, or 4, illustrates a cold weld. A cold weld is illustrated in number 2 in the upper right-hand corner here. With a cold weld, the weld will appear rough and irregular, and with the edges not feathered into the base metal. That's indicative of a cold weld in illustration 2. And by the way, if you're looking at this and scratching your head and saying, boy, I sure hope that the FAA picture quality on the test is better than this, it's not going to be. So if you have trouble seeing the detail on these welds, you may just have to memorize which one represents what kind of weld. The FAA may ask you, for instance, which of these welds would be caused by an excessive amount of acetylene. Take a look in the lower left-hand corner at illustration number 3. That weld would be caused by an excessive amount of acetylene, because what you've got here is slight bumps along the center and craters at the finish of the weld. Those are caused by the boiling of the puddle, and that's caused by excessive acetylene being used. Now let's assume that you have a really ugly weld. a really ugly weld, like for instance this one. You've got holes and some projecting globules in that weld. What do you want to do about it? What you want to do is you want to remove all of the old weld, start all over again, and re-weld the joint. What you do not want to do is re-weld right over this to fill in the holes, and you do not want to grind it off and re-weld. What you want to do is remove all of the old weld and start all over again from scratch to re-weld that joint. Let's take a look again in the FA figure pages, this time at figure 45. There's a number of different types of welds shown here, and the FA will ask you about them. For instance, they might say to you, which one of these spots on here, A through G, shows a butt weld? Well, a butt weld is shown at point A on here. And with a butt weld, what you do is you put two pieces of material edge to edge, and then you weld them. They're not lapped over each other. They're simply edge to edge, like they are here, and then they're welded. So the butt weld is shown at point A. They might ask you, on the other hand, which area shows a double butt weld? Well, take a look at area B. With a double butt weld, again, the two pieces of material are put together, not overlapping, but side to side, and you have a bead on both sides of the joint, and that's what makes it a double butt weld, shown at point B. Or they might say to you, which one of these spots shows a lap weld? Take a look at area G. With a lap weld, you've simply got the two pieces of material overlapping each other, and then you weld the joint. So G is a lap weld. Now let's talk about a fillet weld. A fillet weld is basically simply a T-shaped weld, and the amount of penetration that you need on a fillet weld is 25 to 50% of the base metal thickness. That's the penetration you need for a good fillet weld. Let's talk now about corrosion. If you take a look at this area, that's what corrosion looks like. Some types, and the rust or corrosion that occurs with most metals is the result of a tendency for them to return to their natural state. Now, there's two general classifications of corrosion: direct chemical attack and electrochemical attack. Direct chemical attack is what happens when you have direct exposure of a bare metal surface to a caustic liquid or to a gaseous agent. And that would be things like battery acid or caustic cleaning products and so on. And here is a battery terminal where you've got the corrosion appearing because of direct chemical attack due to the battery acid. Caustic cleaning products, by the way, can also cause corrosion. They are corrosive when in contact with aluminum. So you don't want caustic cleaning products to be in contact with aluminum because you don't want them causing the corrosion. Now this is some shiny, bright new aluminum, but let's assume that you accidentally spilled mercury on that aluminum. What's going to happen to you? What you're going to get is rapid and severe corrosion of the aluminum that is very difficult to control. The mercury is going to cause pitting and intergranular attack, a lot of rapid and severe corrosion that is very difficult to control. Let's talk now about electrochemical attack. Electrochemical attack or galvanic action is responsible for most forms of corrosion on aircraft structures and component parts. The corrosion that is caused by galvanic action is the result of contact between two unlike or dissimilar metals. What we've got right here is we have an aluminum skin and we've got a steel bolt, and we've got corrosion where those two metals are in contact with each other. Now, in the corrosion process, you have an anode and you have a cathode. The anode, or anodic area, is the more active metal. That's the one that is giving up electrons. The cathode is the less active area. That's the one that is receiving electrons. And it is the anode, or anodic area, that is the one that corrodes. The cathode, the less active metal, does not corrode. In the galvanic or electrochemical series for metals, the most anodic metals are those that give up the electrons most easily. So let's take a look at a partial list of the electrochemical series for metals. What we've done here is we have arranged them from the most anodic, meaning the most active, down to the most cathodic or least active. Starting with the most active, you've got magnesium. This is only a partial list, remember. Zinc, clad 2024 aluminum alloy, cadmium, 7075-T6 aluminum alloy, stainless steel, and gold, which is very inert, not very active at all. So what the FAA will do to you on the test is they will give you 3 listed materials. For instance, they might give you magnesium, cadmium, and 7075 T6 aluminum alloy and ask you which of those 3 is the most anodic. By most anodic, they mean which one is the most active, the most reactive metal, and that's going to be magnesium. It's the most anodic, gives up electrons most easily. On the other hand, they might give you a different list of 3 materials. For instance, zinc, 2024 aluminum alloy, and stainless steel, and ask you which of those is the most cathodic, meaning the least reactive, the least active metal, the most inert. And of those 3, it would be stainless steel. Now, galvanic corrosion is likely to be the most rapid and most severe when the surface area of the anodic metal is smaller than the surface area of the cathodic material. Galvanic action that is caused by dissimilar metal contact can be best prevented by placing what is called a non-porous dielectric, simply meaning an insulator between the surfaces. An insulator like paper tape, or in this case a metal primer, some kind of non-porous dielectric or insulator between the surfaces. Now, a passive oxide film is not an electrolyte, and a passive oxide film would tend to prevent electrical contact between dissimilar metals, between anodic and cathodic areas. And therefore, if the FAA gave you a list of some different items and asked you which of these would not be a requirement for corrosion to occur, a passive oxide film would prevent corrosion, not encourage it. So a passive oxide film is something that would not be a requirement for corrosion to occur. Let's talk now about intergranular corrosion. This is an example of intergranular corrosion, and basically what happens with intergranular corrosion, or delamination of the grain boundaries, is that the corrosion is attacking along the grain boundaries of an alloy, a metal alloy. Typically, this kind of corrosion, intergranular corrosion, results from a lack of uniformity in the alloy structure. And the reason that the alloy does not have uniform structure is because it was improperly heat treated. So intergranular corrosion is caused by improper heat treatment. Now, intergranular corrosion sometimes can be seen with a surface indication like this. It's pretty clear, but it not always is visible. So you cannot always detect it with the surface indications. It can be going on inside the metal for quite a bit before the indications work up to the surface. Now, let's talk about exfoliation. Exfoliation, you can see it happening right in this area here. The surface is flaking. Basically what exfoliation is the flaking of the surface due to delamination of the grain boundaries. And that's caused by the corrosion residual product buildup, the pressure of that buildup from the intergranular corrosion. So basically pressure is building up of the corroding materials, and it makes the surface flake, the flaking of the surface, because the grain boundaries in the alloy are delaminating. That's one type of corrosion, or actually a couple that we've talked about already, but we also have fretting corrosion. Fretting corrosion is the type of corrosion that you get when you have two mating surfaces that should be and normally are at rest with respect to each other. In other words, they're not supposed to be moving relative to each other. This is part of a crankcase, and it shouldn't be moving relative to the other part of the crankcase. But it is moving. It's subject to a slight relative movement, and that gives you the fretting corrosion. That produces fretting corrosion. And fretting corrosion between closely fitting metal parts is a cause for rejecting the part. It's cause for rejecting the part and going and getting a new one to replace it. Okay, various types of corrosion. How do we get rid of corrosion once we've found it? Well, if you're working with an aluminum surface, and this is part of an aluminum cowling, one way to get rid of it on aluminum is to use aluminum wool. Aluminum wool is used for general mechanical cleaning. We're talking about mechanical cleaning here to begin with, mechanical cleaning of aluminum surfaces. What if you're working instead with steel surfaces, highly stressed steel surfaces? Well, this is a fine grit aluminum oxide paper. A fine grit aluminum oxide paper like this is what you would use to remove corrosion from highly stressed steel surfaces. A fine grit aluminum oxide paper. Now let's assume that you've got magnesium parts like this propeller gearbox, and you want to mechanically remove corrosion from that. You should use a stiff hog bristle brush. Definitely do not use a metallic brush, because remember we said magnesium is a very active metal, and using a metallic brush can cause corrosion even while you're trying to remove it. So if you're going to remove corrosion mechanically from magnesium parts, you want to do it with a stiff hog bristle brush, definitely not any kind of metallic brush. Now let's talk about protecting aluminum from corrosion. What we're seeing here is an electrolytic treatment, anodizing, being done at the factory. And what they're doing is creating an aluminum oxide coating on the aluminum. Aluminum oxide is a naturally protective film that forms on aluminum. It can be formed a couple of ways, one by electrolytic treatment at the factory, we call that anodizing, and another one is by chemical treatment out in the field if we need to reprotect the material, and that's called alodizing, and it forms on aluminum and is very protective of the aluminum. So what we're basically doing in the anodizing and alodizing processes is forcing something to form that eventually would form naturally on its own, but we want to control the formation of it. Now, an anodized surface coating, which comes from the factory, sometimes is damaged in service. And if it is damaged in service, it can be partially restored by chemical surface treatment. Now that chemical surface treatment that you're seeing here is called alodizing, done a lot of times with the trademark product Allodyne, and it's a non-electrolytic chemical treatment for aluminum alloys, and the purpose of it is to improve the paint bonding qualities and also to increase the corrosion resistance. So alodizing, and it's very easy to get alodizing and anodizing confused, but alodizing is a non-electrolytic treatment. It is a chemical surface treatment for aluminum alloys, and it does improve both the paint bonding qualities and the corrosion resistance of the aluminum alloys. You also need to know that alodizing is done by, or Allodyne is applied to aluminum alloys by dipping them as you're seeing it done here. Now, what if you need to clean or remove corrosion from the surface of anodized aluminum? Well, there are acceptable materials you can use to mechanically clean an anodized surface, and there are definitely some unacceptable ones. Two of the acceptable mechanical products for cleaning anodized surfaces are aluminum wool and fiber bristle brushes. However, you would definitely not want to use steel wool or steel or brass wire-type brushes, because those would scratch the surface of the anodized coating and contribute to galvanic corrosion. So for cleaning an anodized surface, you would want to use aluminum wool or a fiber bristle brush. Now, suppose you want to protect steel tubing. How do you protect the interior surfaces of sealed steel tubing like this? Well, the way you do that, the best way, is a coating of hot linseed oil. What you do is force hot linseed oil in there, get it drained out, and then plug those drain holes. And that's the best way to coat and protect from corrosion the interior surfaces of sealed structural steel tubing. That's a mouthful, isn't it? Let's talk now about stress corrosion. Now, stress corrosion you only get when you have tensile stress on a material. And you certainly have that on a propeller, because centrifugal force is practically trying to rip those blades out of the hub. Stress corrosion happens when you have a corrosive material there, like water or something getting in. You get maybe a little crack that is started, and that crack propagates very rapidly along the end of it. Rather than getting wider, it gets longer. A very common place to find that with a propeller, particularly a constant speed propeller, is right about where the bearings are, where that propeller goes into the hub. A common area for stress corrosion. Now, how do you get increased resistance to stress corrosion cracking? One way to do that is by creating compressive stresses on the metal surface. And you do that in many cases by shot peening, kind of almost like sandblasting it, and that will clean it up and also put a compressive stress on the metal surface. What that means is that the compressive stress that you just put on by shot peening has to be overcome by the tensile forces before the surface of that metal is going to see any tension stress in the future. Let's talk about preparing an aircraft for storage. You're not going to fly it for a while, you're going to store it. You want to prevent corrosion on the engine. So what is done is the cylinder interiors are sprayed with corrosion preventive mixture, and you start out spraying that in through the spark plug holes. Now, once you've done that, you spray it in through the spark plug holes and then rotate the engine and spray each cylinder. But after you've done each cylinder, you go back and do a final spraying. And once you've done the final spraying for the whole engine without moving it, it's important not to rotate the propeller shaft after that final spraying of corrosion preventative into the cylinders. Because if you do rotate it, the seal on the corrosion preventive mixture will be broken, and air will be able to get in and cause corrosion inside the engine. So after the final spraying of corrosion inside the engine, don't rotate the propeller shaft. You don't want to break the seal on the corrosion preventive mixture. Let's talk about cleaning aircraft. First of all, soap and water cleaning, which is what we're about to see here. If you're going to apply soap and water to plastic surfaces, such as, for instance, the windshields, you want to flush the plastic surfaces with fresh water first to prevent scratching. Plastic windshields, plastic windows, any kind of plastic surface is very subject to scratching from all the little fine grit and dust that's going to be on it. And if you're going to start rubbing it with a soap and water mixture, you want to flush the surface first with fresh water and try and just flush off as much as you can that grit and dirt so you don't end up with scratches on the plastic surface. Now let's assume that you've got a tire that's become covered with lubricating oil. What do you do about that? Well, you wipe it with a dry cloth and then you wash it down with soap and water, and that should prevent the deterioration of a tire that's become covered with lubricating oil. Wipe it with a dry cloth, then wash it down with soap and water. Chemical cleaners of various sorts can also be used. For instance, here's our magnesium propeller gearbox again. The magnesium engine parts can be cleaned by first washing them with solvents, then decarbonize them to get the built-up carbon off, and you do that with a hot dichromate solution, and then scrape or grit blast the part in order to finish cleaning it up. So if you're going to clean magnesium engine parts before painting, what they want you to use a dichromate solution. That dichromate solution is a decarbonizer. It gets rid of the carbon buildup on the parts. Now another cleaner is aliphatic naphtha. Aliphatic naphtha is a solvent that they recommend for use to wipe down clean surfaces just before painting. We clean surfaces for painting, and it also can be used, by the way, to clean acrylics and rubber. Aliphatic naphtha would be the cleaner of choice for acrylics and rubber. Another solvent is acetone. Acetone is the recommended solvent that you would use for removing grease from fabric before you dope the fabric. So you'd use acetone to get the grease off the fabric before you dope the fabric on the aircraft. Now, when you're doing chemical cleaning with one solvent or another, fade surfaces, as they will say on the test, cause concern. Now, what are fade surfaces? Fade surfaces are ones that are very tightly joined, as in lap joints. This is a lap joint right here, and the problem with fade surfaces like that is when you're using chemical cleaners, they can get trapped in those surfaces there, between those two lapped surfaces, and that can cause corrosion. So fade surfaces cause concern when you're doing chemical cleaning because of the danger of entrapping the chemicals, corrosive materials, and causing corrosion in those tightly fitting surfaces, and the problem of getting rid of it and getting it out of there so that it doesn't cause the corrosion. As you might guess, you have to be careful applying chemical cleaners. For example, if you're using a flammable chemical cleaning or depainting agent, you'll want to use cotton fiber wiping cloths. Now, why is it important to use cloths with cotton fibers? Because if you use synthetic cloths instead, they may create a static charge while you're rubbing a surface and ignite the flammable chemical. And what about spraying a chemical with atomizing spray equipment? I'll bet you already know the answer to that. If you atomize a flammable liquid, it's going to make it more flammable and possibly explosive. Not a good idea. And there are very tight restrictions also about atomizing many non-flammable chemicals. So if you're using flammable chemical cleaning or depainting agents, make sure that you're using cotton fiber wiping cloths. Now, another concern with chemical cleaners is to make sure that you're not using ordinary or otherwise non-approved cleaning compounds when you're washing down an aircraft, like when you're cleaning the engine compartment to work on it. If you apply some non-approved cleaners on the metal parts, it can result in hydrogen embrittlement in those metal parts. The chemicals in some non-approved cleaners can react with the metal to form hydrogen gas. And this hydrogen gas is then absorbed into the metal, creating a loss of flexibility. And that can result in cracks or stress corrosion of the metal, something you do not want on an aircraft. So when you're washing an aircraft, avoid the possibility of hydrogen embrittlement in metal parts by making sure that you do not use ordinary or non-approved cleaning compounds. By the way, after you've cleaned a bare metal surface, how do you know that you have it clean enough, say for example, to apply a primer? Well, after you clean bare metal, you'll want to conduct a water break test. A water break test involves putting water on the surface of the metal. If the surface is thoroughly clean, a film of water should rest unbroken on the surface. But if the surface is not thoroughly clean, you'll see a break in the film, like you see right here in the beading and these areas. And that break means there's still some grease or some oil on the metal that needs to be removed. So you use a water break test to make certain that a bare metal surface is thoroughly clean. Let's talk about the different characters of metals. First of all, steel. The Society of Automotive Engineers, SAE, uses a numerical index system to identify the composition of various steels. For example, you might see 4130. 4130 stands for chromium molybdenum steel. The first digit on it indicates the basic alloying element. The second digit indicates the percentage of the basic element in the alloy. And the third and fourth digits indicate the percentage of carbon in the alloy in hundredths of a percent. So in the number 4130, the first number, the 4, indicates the basic alloying element. In other words, the 4 stands for molybdenum. The 1 stands for the percentage of it, 1%, and the 30 is the carbon percentage in hundredths of a percent, so that would be 0.30% of carbon. Now, where is stainless steel generally used? Stainless steel is generally used in the construction of aircraft engine firewalls. Let's talk now about heat treatment of metals. Changing the internal structure of a metal is accomplished by heating that metal to a temperature above its upper critical point, holding it there, and then cooling it under very controlled conditions. The reheating of a heat-treated metal, such as with a welding torch, can very significantly alter a metal's properties in the reheated area. How it alters those properties depends on the temperature of the reheat and the method of cooling. Now, when we talk about the hardness of a metal, what are we talking about? The hardness refers to the ability of a metal to resist abrasion, penetration, cutting action, or permanent distortion. And the hardness of a metal can be increased. It can be increased by cold working the metal, and with steel and certain aluminum alloys, by heat treatment of that metal. So hardness can be increased by cold working or by heat treatment, depending on the metal that you're working with and what exactly you're trying to accomplish. Let's talk about some different ways to cold work a metal. Repeatedly applying mechanical force to most metals, like the twisting going on here, or rolling a metal, or hammering on it, and this one is certainly getting hammered pretty good. Rolling, hammering, bending, twisting, all of those cause a condition commonly known as cold working, or strain, or work hardening, and those are just simply different ways to increase the hardness of the metal. Now, one heat treatment process is tempering. And what tempering is it's a process that relieves brittleness and internal strain inside the metal. The steel is heated in a furnace to a specified temperature, and then it's cooled in some kind of quenching solution, air, oil, water, or some special solution, again, depending on exactly what effect you're going for. The reason that steel is tempered after being hardened, and it usually is tempered after being hardened, is to relieve those internal stresses that build up in the hardening process and also to reduce the brittleness. So steel is tempered after being hardened to relieve internal stresses and also to reduce brittleness. Now, two other heat treat processes are annealing and normalizing. Annealing and normalizing remove the internal stresses in metal. And with both of these, basically what you're doing is heating the metal up and then cooling it down under controlled conditions. Now, the effect of annealing, in addition to that decrease in internal stress, is a softening of the metal. But what annealing does not produce is it does not improve the corrosion resistance of the metal. So they're going to ask you about the annealing process of steel and what are the characteristics that you're going to have of that annealing process during and after the steel has been annealed. So some characteristics are that it will be slow cooling and that it will have low strength. The steel will cool slowly and have low strength because of the annealing process during and after it's been annealed. Now, as far as normalizing is concerned, it's good practice to normalize a part after you've welded on it because the process of normalizing it relieves internal stresses. Basically, as we've said, what you're doing is heating the part up and cooling it down under controlled conditions to relieve those internal stresses that have developed in the base metal of the part that you've been welding on. Now, another heat treatment process is case hardening. These gears would have been case hardened. And what case hardening produces is a hard, wear-resistant surface over a very strong, tough core of metal. The steels that are best suited for case hardening are low carbon and low alloy steels. Low carbon and low alloy steels. And the reason that low carbon steels are best suited for case hardening is that in case hardening what happens is the surface of the metal is changed by chemically introducing a high carbide or nitride content. And so essentially what you end up with is the interior of the metal is very tough and strong. The outside of it gets hardened by having more carbon added to it, more high carbide or nitride content, and so you get both qualities that you're looking for. You get a very hard outside surface and you get a very strong core of material. Now, nitriding is a case hardening process that forms a hard case on a part to resist wear by putting a high nitride content in the surface of the material. Let's move on and talk about aluminum and aluminum alloys. Aluminum and aluminum alloys are designated by a 4-digit index system. We've got a 4-digit index system to tell us about the content and type of the alloys. Now, the system is broken down into 3 basic distinct groups. You've got a group that starts with the number 1 and then has 3 digits after it. You've got a second group that starts with the number 2 or something up through 8. And you've got a third group, currently not used, which starts with 9 and has some digits after it. That's available, but it's not currently being used. For instance, if you had a group 1100, what the first 1 is going to tell you is that it is basically commercially pure aluminum. The first digit of the designation identifies the alloy type, which is what you would find in the 2 through 8 group, but the first group, the one that starts with a 1, basically indicates that anything in here, anything starting with a 1, is essentially 99% pure aluminum. So if you're given aluminum that says it's 1100, that's 99% commercially pure aluminum. Now, in the 2 through 8 with some numbers after it group, the first digit indicates the major alloy element that's used in the formation of the alloy. And the 2 that you need to know about on that are, if it starts with a 2, it's got copper as the alloy. If it starts with a 7, it's got zinc as the alloy, and those are the 2 most common that you're going to run across. So 2 with some numbers is a copper alloy. It has got copper as the alloy. 7 with some numbers, zinc is the alloy in with the aluminum. Now, let's assume that they say to you that you have 2024 aluminum. What is the major alloy? Well, if it's 2024 aluminum, the first digit is a 2, and if the first digit is 2, what's the major alloy? The major alloy is going to be copper, because any aluminum alloy that starts with a 2, copper's the main alloy ingredient. If the designation starts with a 7 instead, then it would be a zinc alloy as the main alloying element. Now, some aluminum is described as alclad. Alclad aluminum means that what you have is pure aluminum on the surface layer clad over the top of an aluminum alloy core. So you've got pure aluminum surface layers on an aluminum alloy core. And why would you do that? Basically because pure aluminum is too soft to be using. The aluminum alloy is what you have to use, but the pure aluminum, you can't use it by itself, but if you use it as the surface layer, pure aluminum is pretty corrosion resistant, and so what you use is alclad, so you get the corrosion resistance of pure aluminum on the surface, and then you get the strength of the aluminum alloy in the core material. So let's assume that they say to you that you have a material that is called alclad 2024-T4, and they want to know what exactly that means. Well, the alclad means that the surface of the material is pure aluminum, and it's got an aluminum alloy core. The 2024, the first digit is a 2, and that means that the major alloy is going to be what? It's going to be copper. It's a heat-treated aluminum alloy because it's got a -T4 at the end of it. The -T4 indicates that that particular metal has been heat-treated. So you've got alclad, you've got commercially pure aluminum on the surface, you've got an aluminum alloy core, and the major alloy is copper, and the -T4 means that it has been heat-treated. Let's go into more detail about the hardness and temper designations. As we've just discussed, a letter and often a number combination is placed after the alloy code to indicate what processes have taken place and the degree and the method of hardness. Here's the basic designations. F stands for as fabricated, F for fabricated, meaning it's had no treatment at all. O stands for annealed. H stands for cold worked or strain condition. W is unstable condition, temporary condition. And T, as we saw, means solution heat treated. Now here's an example of what the FAA may ask. They will give you some aluminum alloy designations. For instance, 3003-F, 5052-H36, 6061-O, and they'll ask you which one of those indicates that the metal has received no hardening or tempering treatment at all. Well, which one of those letters, F, H, or O, stands for as fabricated? F does, F for fabricated, and that means that the 3003-F aluminum alloy has received no additional treatment at all. Now what you're seeing happen here is quenching. And what quenching is the process simply of cooling heat-treated metal in a liquid bath of one sort of liquid or another. With aluminum alloys, rapid quenching is needed in order to keep the alloy grains very small. Now, why do you need to keep the alloy grains small? To prevent intergranular corrosion. If the metal cools down very slowly, what tends to happen is the alloy grains get quite large, and there is enough difference in the metals to actually set up corrosion because of large-sized grains of the alloy. So you want to keep the alloy grains small to prevent intergranular corrosion, and to do that, what you have to do is quench the metal very, very quickly. Now, the FAA is going to be hammering home on that idea in a number of questions phrased a number of different ways. For instance, they'll say, you're going to transfer aluminum alloy. They may name it 2024, for instance, they may not specify which alloy. You're going to transfer it from the heat treatment to the quench tank, and it must be done quickly, they say, and they ask why. The reason it has to be done quickly is to attain good corrosion-resistant qualities, because the quicker you do it, the smaller the grains are, and the less likely you are to have intergranular corrosion. Or they might say to you, if too much time is allowed to elapse during the transfer of an aluminum alloy, they may name it 2017, 2024. They may not name it. They may just say aluminum alloy. From the heat treatment tank to the quenching tank, what could it result in? Well, if you let too much time elapse, it could result in impairing the corrosion-resistant qualities of the metal. Again, because if you don't quench it fast enough, the alloy grains will grow large, and the larger they get, the more likely intergranular corrosion is to occur. Now, you might have some metal parts that you heat treat in a sodium and potassium nitrate bath. If you do heat treat parts in a sodium and potassium nitrate bath, you've got to be very careful to rinse those parts thoroughly in hot water after you're done with all the treatment in order to prevent corrosion, because you don't want corrosion to occur from the solution that you use for the actual heat treatment itself. In that kind of bath, sodium and potassium nitrate, you got to make sure that you rinse them off, the parts off very thoroughly with hot water so you don't get any corrosion. Now, some metals can be reheated over and over again, and some metals cannot. One metal that cannot be reheat treated is clad aluminum alloys. Clad aluminum alloys cannot be reheat treated repeatedly without having harmful effects, because what happens with clad aluminum alloys, remember, a clad alloy means you've got pure aluminum on the surface and an aluminum alloy core. And when you keep reheating them, the pure aluminum and the aluminum alloy tend to intermix, and that degrades the quality of the metal. Now, they're also going to ask you about aluminum rivets, 2024 aluminum alloy rivets. And they want you to know that 2024 rivets need to be driven within 10 minutes after they've been quenched. Now, what if you don't drive them that soon? Otherwise, they have to be reheat treated before they can be used, because if you do not drive them within 10 minutes after they've been quenched, then you lose the physical properties of the rivets that you need, and you're going to have to reheat treat it before you're going to be able to use it. And that's what the FAA wants you to know about materials and processes.